Uh, Hello, this is the revision and try to summarize all the takeaway points for all of you. And these are all the most important things I'm going to examine you in the AA. So the outline of the first week, you can see we introduced the definition of ceramics and we talked about what are the ceramic structures and including these nano structures, microstructures. So all this, please make sure you understand it. And the traditional, and also talk about the traditional and the advanced ceramic, the difference between two of them, and also the summaries. And the second section is more important, which is the crystal structures of the ceramics. So we need to understand what are the factors affecting the structures. So there's some examples of the binary ionic compound and the composite of the crystal structures also, and followed by the characteristics. Okay, so the section 3 is not really required. So basically just some introductions of different applications. So you can just quickly go through by yourself. So the objective of this portion, basically the week 1 is please understand the chemical bonds in the ceramics, understand the concept of the crystal structures in the ceramics, and also please know how to calculate the minimal ions radius ratio for Cornish number. But please be reminded in this year we won't test this. And also understand the crystal structures of some typical ceramics and the characteristic, as I just said. Okay, the characteristic you have to know, right? But the application, I just leave you to figure out by yourself. It won't be tested. So these are the summaries. Okay, so we said the crystal structure was determined by three things: the charge balance, the RC over RA, and the third one, which is ionic bond, because we use this geometry to determine the RC over RA and to determine the coordination number. We have to be very careful. So that one only applies to very ionic bound situations. Okay, so just be careful with that one. And we also know what are the rock salt structures. Rock salt, which is coordination number 6. So more or less like two FCC just intersecting with each other. And cesium chloride, which is very much like a BCC. Remember, use BCC to remember this. But of course, it's not a BCC, right? Because the body one is different atoms. So you can see the body one here. Okay, so the zinc blend, which is actually supposed, if we only use the RC over RA to calculate, it's supposed to have coordination number which is 6, but simply because zinc blend, zinc sulfide, they have more covalent bond between this zinc and sulfide, so that's why the coordination number changed to 4. Okay, so this is a special case. This number 4 is a special case. Okay, so also please remember this. And also we talk about the perovskite structures, the ABO3 structures. Okay, so in this case, please know how to calculate the numbers of atoms in one unit cell. Just as we said, if it's a corner is considered as 1 of 8. If it's edge is considered as 1 of 4. If it's face, considered as 1 out of 2. And if it's body, it's very obvious it is 1, considered as 1. So the week 2, we have this 3 parts: introduction, followed by the powder synthesis. In the powder synthesis, we'll talk about background, solid state reaction, and ball milling, and also the summaries. And the sintering is the most important thing. Okay, so the sintering is the most important thing, the essence of this course. And we talk about the sintering, what are the introductions, what are the solid phase sintering, liquid phase sintering, and how can we control the microstructures, and followed by some summaries. Okay, so the learning objective of this, which is please understand what is the basic root of the process and ceramics. Okay, the basic root. And also the steps in solid state reaction. So please remember, process ceramics. If you want to make it a bulk ceramics, you can just use a bigger cake bake a cake as a help you to remember this. Okay, and understand what is liquid phase and what is solid state centering. Okay, this is very important, and understand what is occurring during this centrings. Okay, so what is occurring during centrings is trying to reduce the total surface energy, I will say, right? So we said there's two routes to reduce the total surface energy. Am I right? Okay, so then followed by this for this number 5, explain the migration paths of particles and vacancies in the uh, in this centrings. Okay, so this is super important. Please remember this. Okay, because how particle and frequency move, they just move in the opposite directions. So please understand 5 atomic mechanisms during centrings. So then what are the factors determining the centering products? And describe various mechanisms in the liquid phase centering, understand relationship between the design microstructures and the summaries. Okay, so what are the basic routes? So basic route basically just ball milling, followed by sieving, followed by shape forming, last followed by the centering. Of course, some still need a post treatment. Okay, ball milling. So what is ball milling? So ball milling is simply just rotation raw powders in the grinding media. And what's the purpose of ball milling? It's trying to reduce the size of the coarse particles. Okay, as we have learned later, right, we know that once we reduce the particle size, we're going to have smaller particles. Normally, it's going to enhance the densifications because you start with smaller ones, which means you're going to have more surface area to reduce from. And the classic solid state reaction is A plus B equals to AB, right? We have done quite a lot of calculations in the tutorials, but anyway, in this year, we want test any tutorial. We won't test any of these calculations. And the post treatment to tune the stoichiometries, because most of the time you want A B, but sometimes you get A B 0.9. Okay, it's not 1 anymore. Okay, so you have to find a way to post treatment to tune the stoichiometries. So I've given examples in the notes. Okay, so the summary, that's the ultimate goal for centering basically is to reduce total energy surface. Am I right? Okay, the two routes, one route is coupling, the other route is densification followed by the grain growth. And there's two centering, which is liquid and solid centering. And the Young surface equation, Kelvin equation, okay, so these two derivations and how can we apply is not required. But remember this one, free energy of one atoms, which is highest at the mountain, followed by the land, followed by the valley. Okay, so the reason behind it is simply because if it's a mountain, which is convex case, R is larger than 0. For the valley case, R is less than 0. Okay, and these are there also another way of this Young's equation. So we have two ways. So remember this one. So this one is also a Young's equation. So anyway, it tells you the same thing, which is free energy per atoms is inversely proportional to R. Okay, so in thermodynamic, we must know that the atom with larger mu is going to escape to where the mu which is smaller. So that is this case, right? So smaller one, you're going to have higher free energy. So it's going to round towards the big ones to merge as even bigger ones. Okay, so this is auto-rappelling. So the summaries. So okay, the centering driving force is reduced surface energy by coupling and the densifications. Okay, Young's surface equation. Okay, so atoms move from convex to flat to concave. Vacancy is opposite. Okay, so 5 atomic mechanisms. We said 1, 2, 3. What are the one? One is evaporation condensation. So atoms condense from vapor to the neck. Neck is always the low energy side. Okay, surface diffusion. Atom move from surface to the neck. Volume diffusion, which is also moved from the surface to the neck, but it is below. The root is a little bit different. Okay, so this 1 to 3 is only give you coupling. Okay, because it does not involve with any vacancy movement. But P4 and P5, because P4 and P5 you're going to have grain boundary. Okay, grain boundaries. Grain boundary is very important because the grain boundary is the first starting point between these two particles, right? So everything have to go through these grain boundaries. Am I right? Because this is the shortest route between these two particles to swapping around the particles and vacancies. Okay, so basically what happens during this grain boundary diffusion? basically their atom move from the grain boundary to the neck, and vacancy move to the neck to the grain boundaries. Okay, so only when you have this opposite flow, you are going to have densifications. Okay, so this is a very important thing. Atoms have to be moved from grain boundary area to neck, and the vacancy move from the neck to the grain boundaries. Then by doing so, the vacancy is going to be filled by the atoms to induce these densifications. Okay, some general points. Okay, so during the sintering, we prefer the higher temperature because high temperature is going to give you a higher bulk and grain boundary diffusion. In general, this is going to enhance densifications and enhance the grain density uniformity, and also reduce the agglomeration. Is also going to enhance densifications. Okay, impurities. Okay, so some impurities may suppress the coupling and the grain growth and lower the grain boundary mobilities. Okay, so if you still remember one route, right, we said we have to make sure you have densification first, followed by the grain growth. Instead of at the very beginning, you start with grain growth. Okay, so that is a very important thing. So in certain cases, we have to put impurities there, so to suppress the coupling, to suppress the grain growth, to let the densification happen first. Okay. And certain gas, okay, so if you use a solid state reaction, remember, so the gas need to dissolve the solid to reduce pores. This is also very easy to understand, right? If the solid gas does not dissolve the solid, which means solid cannot pass through the gas to move to the preferred site. Okay, so this is another thing. Some large particle distribution will also promote the abnormal growth. This is make sure if you want a uniform structures, make sure you have a very small particle distributions. Okay, so these are the summaries for this the solid state sinterings. Okay, so we move to the liquid phase. Okay, liquid phase. The major difference between the liquid phase and the solid phase is this what? Keywords is large capillary force. And large capillary force must be induced by what? And also wetting, wetting. Wetting is very important. If it's not wetting, actually it's even worse. You just pull them away instead of just attract them closer, enhance the densifications. Okay, so we said what happens in the liquid phase sintering. Okay, so at the very beginning, particle come closer very fast to densify first, then followed by this solution precipitation, and the last stage is skeleton sintering. Okay, these are three stages during the liquid phase sintering. But what's really make the liquid phase different from the solid phase is this first one. First stage, which is particle rearrangement. So the particle rearrangement is very, very fast in the liquid phase because of this large capillarity force. Okay, so of course, if you want very high densifications, make sure there's a four conditions during liquid phase sintering need to be met. Okay, so please go through this by yourself. I'm not going to explain anymore. Okay, so this is a very important one. Okay. And also we mentioned liquid phase is very nice because it can enhance densifications. That is very much wanted in many applications, but be very, very careful. There's no perfect thing for anything. Okay, so you have to be very much control what you want. So in many applications, because no matter what, you're going to have impurities, right? Because without this impurity, you won't have liquid phase. So in the end, this impurities is going to end up in the grain boundaries. So this very disordered grain boundaries because of this impurity, so it's going to make it very harmful for many applications. Okay, so we listed two applications. Okay, in the notes, please go through by yourself. So that's the last part. Also, we have to be very aware of this one. The property is very much microstructure dependent. Okay, so please be very, very careful. But in the exams, I normally will tell you what I need. Okay, so instead of just you don't really need remember all these details, what type of structure is needed for what type of applications. So in the examination, I'm going to give you what type of exactly the structure I need. Okay, but please read through this by yourself.